I'm going to change the share to my Elmo. And we're looking at number 15, right?
Yeah.
Okay, which reads nitrogen monoxide reacts with oxygen to give nitrogen dioxide. They give the reaction equation. You wish to react nitrogen monoxide and oxygen in the correct stoichiometric ratio. So that means you want to have both of them used up completely and nothing left over.
Okay.
The sample of nitrogen monoxide has a volume of 150 milliliters. What volume of O2 is required at the same pressure and temperature? And then finally, what volume of nitrogen dioxide at the same pressure and temperature is formed in this reaction?
So
Okay.
we would use PV equals nRT.
What's that?
Would we use PV equals nRT for this?
Not necessarily. So 15. There we go. I don't know why this is zoomed in so much. Okay. So number 15, the reaction is 2 nitrogen monoxide react to give you, might as well start over. I got plenty of paper. Two nitrogen monoxide react with oxygen to give you, and that should be monoxide, not dioxide, to give you 2 nitrogen dioxide. And for A, you want stoichiometric amounts. And for the NO, we have 150 milliliters. And we have a certain pressure and we have a certain temperature, but we don't know what those are. And for O2, we want to know how many milliliters, and they're at the same pressure and temperature. All right.
Okay.
So this is basically a reaction that's happening in a bag. Okay, a reaction that's happening in a bag. So what happens when you think about a bag? So here's a bag, and you have pressure from the atmosphere pressing down on the bag from all directions of one atmosphere, right?
Okay.
So this is like you're a bag, only you're not a bag of gas, you're a bag of, liquid, solid, and all sorts of different things. But imagine that this is just a bag with gas in it. Now, if the bag is also pressing out with 1 atmosphere of pressure on all surfaces, the bag is not going to get larger or smaller because the counter pressure is 1 atmosphere. Are you with me there?
Mm-hmm.
Okay, so as the reaction goes on, you can see that we have 3 moles of gas here, and we're making 2 moles of gas. So what's actually going to happen to this bag is that as you get rid of 3 moles of gas and only make 2, the bag will actually get smaller because the pressure is proportional to the moles of gas. So this equation is good for gases and gas mixtures. The pressure when you have 3 moles of gas will be different than the pressure when you have 2 moles of gas. So when this reaction gets done, the pressure will actually be less. So I'm going to make the bag the same size. So that's supposed to be the same size here. We have 1 atmosphere of pressure pushing and 1 atmosphere of pressure pushing. But inside the bag, since we only have 2 moles for every 3 moles we started with, we only have 2/3 of the pressure that we originally had, which would be 0.67. So inside the bag, it's pressing out, not with 1 atmosphere, but a little less. So what's going to happen to the bag? The bag is going to shrink in size, because we know that if the volume goes down, the pressure will go up. And it will continue to shrink in size until there's 1 atmosphere of pressure on the inside. So this is the understanding here of what's happening. And here, I just use 1 atmosphere because that's the pressure that we feel on a day-to-day basis. So it seemed like that would be a relevant pressure to use. We could have done this for any pressure, though. I could have put 2 atmospheres here, 2 atmospheres here, and 2 atmospheres in the bag. You with me? Okay, so that being said, if we think about this, you can see that since the pressure is constant, I'm going to put K there. Since the moles are constant, because, well, actually, the moles are not constant. I take that back. The temperature is constant. You can see that basically, oh, and R is constant, right? You can basically see that the volume is going to be proportional to the moles. Okay. Now, when we read this equation, we normally think 2 moles of NO plus 1 mole of O2 gives you 2 moles of NO2. That's the way we normally think of coefficients, correct?
Yeah.
However, these are just proportions. And since these proportions, moles, are proportional to volume, we can also say 2 liters of NO would react with 1 liter of O2 to give us 2 liters of NO2. We can do the same thing. And remember how I said this volume would be about 1/3 of the original volume?
Yeah.
Can you see how this 2 is 1, or excuse me, I said 1/3, I meant 2/3. Can you see how this 2 is 2/3 of 2 plus 1, the original volume?
Okay.
Now, we could also do this. 2 milliliters of NO plus what?
1 milliliter.
1 milliliter of O2 gives me what?
2 milliliters of NO2.
2 milliliters of NO2. I can use any volume I want here as long as I use the same volume for every coefficient.
Okay, so it's just a proportion of them.
It's just a proportion. So in this case, if I want to know how many milliliters of O2 I need for my milliliters of NO, I'm just going to do this. 150 milliliters of NO times here, 1 milliliter of O2 for every 2 milliliters of NO.
Right.
And we're going to get 75 milliliters of O2.
Okay.
Now, let's do it the other way with the PV equals NR2 way, because we can still do that. And let's see if we get the same answer. And let's see if it's as easy to do.
Okay.
So when you ask, can we use PV equals nRT? And my answer was, well, yeah, but, and there was the definite hesitation, but I don't want to.
Why not? We just did.
No, we did not use PV equals nRT. We just used this. There's your answer right there.
Oh, right. I mean,
And this, you want to show this.
Behind it, though.
Okay, so let's use a PV equals nRT. And remember, for the NO, we've got 150 milliliters, we've got a pressure, and we've got a temp. And we don't know what the pressure is or the temp is, right?
Yeah.
And for the O2, we don't know how many milliliters, and we have a pressure and a temp.
Mm-hmm.
So this is the way we could do it. We could, 1, calculate the moles of NO, then 2, calculate the moles of O2, and then 3, calculate the volume of O2. So let's calculate the moles of NO.
Okay.
1. So for the moles of NO, I'm going to use N is equal to PV over RT. So all I've done is I've taken the ideal gas law, PV equals nRT, and made it focus on N. So here I get P times 150 milliliters over RT. Now we can put a number in for R, right?
Yeah.
What number do we put in for T?
T?
We don't have one.
Right.
What number do we put in for P? We don't have one. So I'm just going to leave it the way it is.
Okay.
So this is the moles of NO.
Okay.
Now, the moles of O2 are going to equal the moles of NO times 1 mole of O2. So I'm going to put X here to 2 moles of NO, right? Okay, so let's plug in the numbers. We actually have P times 150 milliliters over RT moles of NO. And that's moles of NO. We just calculated that, right?
Yeah.
Okay, now we're going to multiply by 1 mole of O2 to 2 mole of NO, and you can see that these cancel. So now we're left with P times 75 milliliters, because 2 goes into 150 75 times, right? And RT. Are you with me there? Yeah. And then 3, we're going to calculate the volume of O2. Now, the volume of O2 is going to be equal to nRT over P, right?
Yeah.
And this is the moles of what?
O2.
O2, which we know is this, P times 75 milliliters over RT. Now we have to multiply that times RT over P from over here, because all of this is N.
Yeah.
Now let's take a look at when we multiply these. What happens to the R's?
Cancel.
They cancel. What happened to the T's?
Cancel.
What happens to the P's?
Cancel.
And we're left with 75 milliliters. So I guess the real question is, do you want to do it this way using PV equals nRT and these abstract ideas of P and T without knowing what they are? Or do you just want to realize that, you know what, in this particular situation, since the pressure is constant and the temperature is constant, that means the only other two, and well, R is constant, right?
Mm-hmm.
The only 2 other variables are V and N. That means that V is proportional to N, and coefficients are volumes also. Okay? Guess what happens if V is constant, T is constant, and R is constant? Not P, but V.
Then P is proportional to N.
Right. And the coefficients are therefore
Pressure.
pressures. So I think that this is a far more convenient way to do this problem. And they're trying to get you to think about this type of situation. So can you use PV equals nRT? Yes. Do you want to use PV equals nRT? No. Okay?
All right.
All right, now that's A. Now, for letter B, 15B, they ask what volume of NO2 at the same pressure and temperature is formed in this reaction. So here's the reaction again, 2NO gas plus 1O2 gas gives you 2NO2 gas. We know that it's 150 milliliters here, and we know it's 75 milliliters here, and we know it's constant pressure, constant temp, and constant R, right?
Yeah.
That's kind of redundant because R is actually the gas constant. So you're saying constant gas constant. But the only things that are changing are volume and moles, right?
Yeah.
So with these being constant, that means that volume is proportional to moles. So the coefficients are mole ratios, but they're also volume ratios. And the neat thing about volume is there's many different types of volumes we can use. It's our choice, but there's only one mole we can use, right?
Yeah.
What I should really be writing here is that the coefficients are amount ratios
Yeah.
and volume ratios. Because when we talk about amounts, this two could be two, just two. Two of these and one of these make two of these. Or it could be 2 dozen of these, react with 1 dozen of these and make 2 dozen of these. Or I could say that 2 represents 20. So 20 of these react with 10 of these to give me 20 of these. Or more commonly in chemistry, 2 mole plus 1 mole gives you 2 mole. Fair enough?
Yeah.
Okay, so our question is how many milliliters? I want to make sure that this is what they're asking.
Yeah.
They ask you what volume of NO2 is being formed here. So we don't need to answer in milliliters if we don't want to. But I think I want to, given that these amounts are given in milliliters.
Right.
So let's start off with 150 milliliters of NO. What are we going to multiply by?
2 milliliters of NO2.
Over?
2 milliliters of NO.
Okay, and these cancel, and we get 150 milliliters of NO2. Now, remember how we said that we're using a stoichiometric amount of each?
Mm-hmm.
That means none of them, nothing's left over. So that means we could have started with the 75 milliliters of O2, and let's see what we get for that.
That's what I did.
Okay, and what did you get?
150 milliliters of NO2.
Right, because it's 2 moles of NO2, or excuse me, 2 milliliters over 1 milliliter of O2, and you get 150 milliliters of NO. So it doesn't matter where you start with O2 or NO, you're going to get the same answer either way.
Right.
The mistake would be to say, okay, if I start with 150 of this, I'm going to get 150 here. If I start with 75 of this, I get 150 there. So therefore I get 300.
Right.
That's a mistake. It's kind of like saying, you know what, if I start off with 2 slices of bread, I'm going to get 1 sandwich. If I start off with 1 slice of bologna, I'm going to get 1 sandwich. And therefore I start off with 2 slices of bread and 1 slice of bologna. I'm going to get 2 sandwiches.
So
And you're not. You're going to get 1 sandwich.
why is there a loss of product?
There is no loss of product.
Okay. A loss.
I mean, why do you say there's a loss of product?
I was just kind of wondering, like, conceptually, how come they don't add up? How come the product amount doesn't add up to the?
Well, let's take a look at that. What is the structure of NO? It looks like this. Here's an N and here's an O, right? Nope, I made that backwards because oxygen's smaller than nitrogen, right? Going across the period.
Yeah.
So I made this wrong. Here's my nitrogen and here's my oxygen. How many of these do I have? 2.
2.
Okay, now I'm going to react this with oxygen. So here's my 2 oxygens bonded together. And we're doing the space filling models. We're not doing Lewis structures or anything like that. Fair enough?
Okay.
So NO2, nitrogen's going to be the atom in the middle because it likes to make more bonds, right?
Yeah.
So here, nitrogen is going to be the bigger atom and oxygen the smaller one. How many of these do we make?
2.
Okay, now when you said, why are we losing stuff? Your idea was that we have 2 plus 1 making 2. We start off with 3 of these things and we end up with 2, right?
Yeah.
Is that how we balance equations? Just by looking at coefficients?
Yeah.
No.
Look
We
like
balance things by looking at how many atoms you have of each.
Oh, yeah.
How many nitrogen atoms here on the left?
2.
How many on the right?
2.
How many oxygen atoms total on the left?
4.
How many on the right?
4.
So did we start with 2 nitrogens and 4 oxygens and end up with 2 nitrogens and 4 oxygens?
Yeah.
Have we lost anything? And the answer is no. All we've done is we've taken 3 things and recombined them, so now they're 2 things.
Okay.
So it's almost kind of like a question you might ask where, just to be really frivolous, I take flour, sugar, butter, chocolate chips. That's basically enough for chocolate chip cookies, right?
Yeah.
I take 4 things, but I make 36 cookies. How can I get 36 cookies out of 4 things?
Yeah.
Well, because when I mix these things together and then reportion it out, those portions are smaller than these were to begin with, right?
Yeah.
So it's the same thing here. You don't want to get caught in the coefficients. Coefficients are how we balance things, but we're using the number of atoms to decide what the coefficients are. We're not saying that the sum of coefficients on one side equals the sum of coefficients on the other. It doesn't work that way. Sometimes it does. Sometimes it does, but usually it doesn't. Okay. So for 15B, I would expect to see that for your answer, or that for your answer.
Okay.
Okay. That being said, what would you like to do next?
Hmm. I guess partial pressure
Partial pressure?
or kinetic molecular theory.
I did some partial pressure problems last night, but there's one that I had a problem with, and it was number 40. And I decided I have a better way to do number 40. So let's take a look at number 40, okay?
Okay.
So here's number 40. A balloon is filled with helium to a volume of 12.5 liters at a pressure of 1 atmosphere. Oxygen is then added so that the final volume in the balloon is 26 liters with a total pressure of 1 atmosphere. The temperature, which remains constant, is 21.5 degrees Celsius. So if we look at A, what mass of helium does the balloon contain? You know, whenever I see that word mass, I start thinking I want to use density is equal to PM over RT. And I think we talked about this equation
Yeah.
where the uppercase M stands for molar mass.
Yeah.
Now, density is also equal to mass divided by volume. So here, we want the mass of helium in the balloon. We can say that the mass of helium in the balloon is going to be PM times V divided by RT. So the pressure is 1 atmosphere. And actually it's 1.00. The molar mass of helium is 4.01 grams per mole. And here when they talk about molar mass, they do mean not what is just the mass of it, but they want to know per 1 mole.
Yeah.
Okay. The volume you can see is 12.5 liters, right?
Yeah.
R, we're going to use 0.08206 liters atmosphere per mole per K.
Right.
And for the temperature, we're going to take that 21.5 degrees Celsius and add 273.15. And we're going to get 294.65 K. When we start crossing things that cancel, atmospheres will cancel, liters will cancel, Ks cancel, and moles cancel, and we're going to be left with grams. And let's go ahead and estimate this. So what is 0.082 times 300? Well, I like to think of 0.082 as 0.1. So what's 1/10 of 300? 30. Now, clearly, it's not going to be 30 because this is 0.08, right?
Yeah.
So what you want to do is, since that's 0.08, you want to drop that 30 by 20%. 10% of 30 is 3, 20% is 6. So we're going to drop our number down to 24 or 25, okay?
Okay.
So we multiply these numbers on the bottom, we get 25. How many times does 12.5 go into 25?
Twice.
Twice. And then how many times does 2 go into 4?
Twice.
Twice. So our answer should be 2, correct?
Yeah.
And when we did this last night, I think it was 2.07.
Okay.
So that's the mass of helium in our balloon.
Okay.
Fair enough?
Yeah.
All right. Now, B asks us, what is the final pressure of helium in the balloon? So for B, we're looking at, we originally have a helium balloon with 12.5 liters and 1 atmosphere of pressure, right? And 294.1565 K.
Mm-hmm.
Now we add oxygen and we've got a bigger balloon. We've got helium, but how many liters of helium do we have here? 26. 26, because the volume of helium is the volume of the balloon.
Yeah.
What is the pressure of helium? Well, I don't know. I do know that the pressure of helium plus the pressure of O2 is going to equal 1 atmosphere, because the whole balloon has a pressure of 1 atmosphere, and the partial pressure of each should add up to 1.
Okay.
And I know that the temperature is 294.65 K.
Yeah.
Now, how many liters of oxygen do we have? 26 liters. What's the pressure of O2? I don't know, but I know when I add it to helium, it should equal 1.
Yeah.
And what is the temperature of the oxygen? 294.65.
Yeah.
We don't know, but we don't know how many moles we have, do we?
No.
Okay, the other thing we know in this case is that, how do I want to say this? Well, we add up these two, we get 1 atmosphere, right?
Yeah.
We also know, since this is a partial pressure problem, that the mole percent is going to equal the pressure percent, right?
Yeah.
Remember how we talked about that before?
They're proportional.
Right.
Okay.
So for this case right here, the mole percent is going to be the pressure percent.
So we need the mole.
Okay, so it seems to me that the way to tackle this, and this is differently than I did it last night, which you can watch the video of. The way to do this would be, first, calculate the partial pressure of helium. And here's what we're going to do. We're going to say that you have helium, 12.5 liters, 1 atmosphere and 294.65 K, right?
Yeah.
And now we're going to say we've got helium 26 liters. We don't know the pressure, so I'm going to put PHE and 294.65 K. So can you see that the helium is going from a volume of 12.5 liters to a volume of 26 liters?
Yeah.
Is that a change?
Yep.
So if that's a change, we're going to use P1V1 over N1T1 is equal to P2V2 over N2T2 for helium. Whose law is that?
I don't know.
Oh, come on.
Is it Boyle's? No.
It's Tony's law.
Oh. Okay.
Now, with Tony's law, what do we get to do to this thing if the moles of gas don't change? And remember, we're taking all of the helium atoms and putting them in here. So the number of helium atoms don't change. What do we get to do with Tony's law when something doesn't change?
Cancel out and
They cancel out. Do the volumes change?
yeah.
Okay, we can't cancel them. Presumably, do the pressures change?
Yeah.
Can't cancel them. Do the temperatures change?
No.
So we can cancel them. So we want to calculate P2, which is the partial pressure of helium in this bigger balloon. And that P2 is going to be P1V1 over V2, which is 1 atmosphere times 12.5 liters over 26 liters. And it's going to be about half of an atmosphere, right? Because 12.5 over 26 is about half.
Mm-hmm.
A little less than a half, though, correct?
Right.
So let's do this. 12.5 divided by 26, and I get 0.48.
So that's the partial pressure of helium.
That's the partial pressure of helium. So that's B.
Okay.
Now for C, they want the partial pressure of oxygen. How are we going to do that? Because we don't have an initial oxygen, do we? We can't do a P1V1 over N1 because we don't know what the original amount of oxygen was. Well, we could figure it out though, couldn't we?
Yeah.
But let's not. Let's do something simpler. And it's written right here up in B. What do we know about the partial pressure of helium plus the partial pressure of oxygen in the final balloon?
They equal to 1 atmosphere.
Right. So couldn't we do that the partial pressure of oxygen is 1 atmosphere minus the partial pressure of helium, which ends up being 0.52 atmospheres.
Mm-hmm.
So this was a lot better than what I did yesterday. It's more simple, more direct. I did all sorts of different things yesterday.
Can we summarize what we just did?
Well, you helped me to summarize. What did we do for A?
Well, we found the mass of helium with the density equation.
Okay, that's a very good summary. We used the density equation to find the mass of the helium. What did we do in B?
Find the pressure
How?
with P1V1 equals P2V2.
Okay, but how did we know to use that and not just PV equals nRT?
Oh, we eliminated the constant.
I kind of want to back it up even more. Didn't we decide that the volume of helium changed?
Yeah.
So therefore, this is a change problem.
Right.
And so therefore we use P1V1 over N1T1 is equal to P2V2 over N2T2.
Yeah.
So first for B, we identified it was a change problem, and then we used the change equation, which I am saying is Tony's equation. It's really the change equation. You with me?
Yeah.
Okay. So I think the summary for B is it was a change, so we used the change equation.
Right.
How would you summarize what we did in C in 2 words? One is possessive and the other
Dalton's law?
Dalton's law. Isn't that what Dalton's law is? The sum of the partial pressures is the total pressure.
Yeah.
So we did we Dalton lawed that on C.
Okay.
Now, what about D? What is the mole fraction of each gas? So for D, mole fraction. Here's how you calculate the mole fraction. It's going to be equal to, so the mole fraction of gas 1, we use the letter X and 1.
Okay.
It's going to be the moles of, I'm going to call this A instead. It's the moles of A over the moles total. That's the mole fraction.
Okay.
Now, remember, in a case like this, we get to use pressures instead of moles if we so desire.
Okay.
So it's also equal to the pressure of A over the pressure total. So if we want the mole fraction of helium, are we going to use the moles of helium, which we never calculated, or are we going to use the pressure of helium?
Pressure?
Right, which is 0.48 atmospheres. Now, what was the total pressure in that second balloon? 1.00. So the mole fraction is 0.48. And it has no units because the atmospheres cancel.
Okay.
Now, what is the mole fraction of O2?
0.52.
Right. Atmospheres over
1.00 atmospheres.
which is 0.52. So remember how I was telling you for these Dalton's law problems that it's the mole percent is equal to the pressure percent?
Yeah.
Well, here the mole fraction is also equal to the pressure fraction. It's the same type of thing. Mole fraction just means out of 1. So I like percentages better than fractions. And I was talking about that last night also.
Yeah.
So like the mole fraction of men in the world is about 0.5.
Right.
So that means 0.5 guy out of 1 person, right?
Yeah.
And that sounds kind of ridiculous. The percentage is 50. So that means there's 50 guys out of 100 people. And that's something we're better at thinking about rather than saying, okay, we're going to let 1 person be the representative person and half of them is a guy. It's kind of, okay, I get it, but why? Okay, so that would be number 40, done, I think, more efficiently, and also capturing the ideas of what the chapter is trying to get us to think about.
Okay.
So I'm glad I had the opportunity to redeem myself. I don't know why I was messing up last night, but I think I was just trying to be too clever.
Okay.
And that's something you always want to avoid, trying to be too clever.
I don't think I have that problem.
Okay, so the rest of these problems in gas mixtures and Dalton's law, you can watch that video. Let's continue with the next section, which is the kinetic molecular theory of gases. So do you know what the kinetic molecular theory of gases are?
Not memorized. I have it written down, but the meaning is a little fuzzy. Oh,
Well, one of the things is that to say it without writing it all out is that the size of the gas particle itself is much smaller than the distance between the gas particles.
yeah.
So that's the way the book would say it. And the way I would say it, just to simplify it, is that gases are mostly space. Now, because of that, what can gases do very easily? They compress. Okay, so that's one of the ideas of the kinetic molecular theory of gases. Another one is the idea that the particles are in constant random motion. So the gas particles are in constant and random motion. So what does that mean about gases when we think about it in a worldly sense? Well, it means that if the particles are always moving around and you have them in a box, when you open that box, what happens?
They go out.
They go out, they spread, right? So I'm going to say gases spread.
Right.
So that's why when you're walking through the women's department at Macy's and all them women are trying on all them damn perfumes, you don't even have to be in the department to smell it because the gases are spreading. You ever notice that in a department store when you get near the women's section, you know you're near it?
Yeah.
Because they're all trying on those fragrances and they spread. But you also notice that the farther away you get, the less you smell it because even though they are spreading, they're getting more dilute.
Yeah.
So I'm always walking way around those areas. I don't like them. Okay, so that's two of them. What's another one?
I don't know. I have written down that the average energy of the particles is proportional to the temperature.
That's a perfect one. So the kinetic energy, so Ke, is proportional to the temp in Kelvin.
Okay.
That's important.
Okay.
Okay, so what can we say about that when we say Ke is proportional to Kelvin? What might that result in? Well,
Higher temperature.
one of the things that you should know about kinetic energy is that it is 1/2, or it is mv squared over 2. M is mass, v is velocity.
Okay.
Okay, so that means that at a given temperature, if the kinetic energy of helium has to be the same as the kinetic energy of xenon, and they're vastly different in size, right?
Yeah.
Helium is 4, xenon is 131.
Okay.
How can 1 mole of xenon have the same kinetic energy as 1 mole of helium when the helium atoms are 4 and the xenons are 131? How can a car, which is huge, have the same kinetic energy as a rock, small rock?
I don't know.
Well, they have different masses, right?
Yeah.
If you have a really tiny mass, how are you going to get a large kinetic energy? What's the only thing you can change in this equation?
Velocity.
It's got to have a high velocity if you have a tiny mass, right?
Yeah.
And if you have a large mass, it has to have a tiny velocity, right?
Yeah.
So what we can say about this is that the velocity of small particles is large or great compared to the velocity of what?
Large particles.
Large particles. So if we want to really think about that a little differently in a real world sense, what does that mean about how fast these gases spread? Which one's going to spread faster? The one that's going faster or the one that's going slower?
The faster one, so smaller.
So small gas particles spread faster than large gas particles.
Okay.
Okay. Okay. And there's one more. And to sum it up in 2 words, the first word is elastic. And do you remember what the last word would be?
No.
Collisions.
Okay.
So if those particles are moving in a constant and random motion, is there the chance that 2 particles may run into each other?
Yeah.
Is there the chance that the particles might run into a wall or a surface of some sort?
Yeah.
Okay, so when it hits the surface, that's pressure that it's applying to the surface, okay?
Yeah.
So you're under 1 atmosphere of pressure right now because a lot of particles are hitting you. You're used to it, so you don't really feel it, right?
Yeah.
Okay, so what would happen if the particles, when they hit you, they didn't bounce off, but they stuck to you? Well, here's the deal. If they stuck to you, they wouldn't be able to come back and hit you again and give you more pressure, would they?
Right.
So eventually, if all the particles lost all of their kinetic energy and they stuck to everything that they landed on, would there be anything such as pressure?
No.
There would be no pressure. So for elastic collisions, that means that gas particles essentially stay as gas particles. They don't become liquids.
So the energy stays the same?
Right. Well, as long as you keep the temperature the same, the energy. So, and this is why a gas becomes a liquid. If you cool it down, you're removing the kinetic energy. And if you're removing the kinetic energy, it might stick to something better.
Right.
So for elastic conditions, we're going to say gases stay gaseous if there's no change in pressure, change in temp. Because what are 2 ways of making a gas not a gas? One is lower the temp. Because if you lower the temp, they lose kinetic energy and they start sticking together because of they might be polar or something like that, right?
Mm-hmm.
Another way to make a gas not a gas is this way. They're mostly space, right?
Mm-hmm.
But what happens if you start squeezing them together and taking that space away? Eventually, what's going to happen?
The pressure increases.
Well, the pressure increases, but eventually what's going to happen with the space between the particles,
They'll come together and stick
it goes
together.
away. And when the particles are touching one another, but still moving, what do we call that?
I don't
A
know.
liquid.
Oh yeah.
And if we continue to squeeze so that the particles can't even move and they're stationary, but they kind of vibrate, what do we call that?
Solid.
Solid. So you can take a gas and turn it into a solid by increasing the pressure. And you have to take away kinetic energy. And the best way to do that probably is lower the temp.
Right.
Now, what happens when you want to get that liquid into a gas? You add kinetic energy to turn it into a gas. All righty. So that's the kinetic molecular theory of gases. And here are some things that you can say as a result of this. And this is the most subtle one, the last one, where we say, hey, gases stay gases if you leave them alone. Very subtle, but important. Because if they did not have elastic collisions, it would mean that gases would turn into liquids as they lose energy. The best example of that is those little rubber balls that you can buy in the grocery store for like a dime or whatever.
Yeah.
When I was a kid, we called them super balls. And they would bounce almost back up to where you dropped it from.
Mm-hmm.
And they would just like bounce forever, and it would just drive the parents crazy. But eventually it stopped bouncing. Why does it stop bouncing? And the answer is it does not have elastic collisions. So if it does not have elastic collisions and gases behave that way, that means gases would eventually stop bouncing and they'd all be on the floor. And you know, with those rubber balls, when they ended up on the floor, they were still rolling around, right?
Yeah.
So if you had a bunch of gas particles rolling around, that'd be a liquid. And then if they stuck together even more, it'd become a solid. So elastic collisions is really important. Gases stay gases when you leave them alone. Okay, so let's take a look at some problems dealing with the kinetic molecular theory of gases. So here's number 42. Equal masses of gaseous nitrogen and argon are placed in separate flasks of equal volume at the same temp. Tell whether each of the following statements is true or false. So let's draw two separate flasks of equal volume at the same temp with nitrogen and argon in it. So this is number 42. Here's my container of nitrogen. And here's my container of argon. They're supposed to be the same size. Here's my argon. And notice here it says equal masses of gaseous nitrogen and argon. So argon weighs 40.
Okay.
And nitrogen weighs 28.
Right.
So what's 5 times 28?
100 and something.
140?
Yeah.
Okay. So I'm going to add one more argon because these are 40. Actually, and one more nitrogen. So what's 6 times 28? Let's do that. 168.
Okay.
And here for the argon, 4 times 40 is 160. So this is pretty close to being the same mass of each. Fair enough?
Yeah.
Okay, so we're going to use this as kind of our idea of what's going on. Equal masses of gaseous N2 and argon are placed in separate flasks of equal volume at the same temp. Okay, so A, there are more molecules of nitrogen present than atoms of argon. Would that be true or not?
Yeah, true.
True. And the reason for that is that each N2 weighs less than each argon, but you have to have the same mass of each.
Okay.
Okay, how about letter B? The pressure is greater in the argon flask. Well, this temperature is equal to this temperature. And what did we say about the kinetic energy? The kinetic energy is proportional to the temp.
Right.
So both flasks have the same kinetic energy for their molecules in total.
Yeah.
So this kinetic energy in this flask is equal to the kinetic energy in that flask.
Okay.
Okay, so it turns out that pressure is going to be proportional to that kinetic energy. So what can we say about the pressure of each?
But there's more nitrogen, so isn't pressure
But what did we say about smaller ones?
they're faster?
They're going faster.
Yeah,
What do we say about big ones?
they're slower.
Okay, so the big ones are going slower, the small ones are going faster, and they offset each other so that they end up having the same pressure. Because, you know, when we're talking about something that's big and hits you slow versus something small and hits you fast, you feel the same pressure.
Okay.
So imagine if, you know, imagine someone walking down the street, a really big guy runs into you and they're just walking down the street. You're going to get knocked back, right?
Yeah.
Now imagine someone your size running at you and hitting you. Are you going to get knocked back?
Yeah.
Okay, and you presumably could be knocked back the same amount by each, right? If the person's going fast enough, and if that big person, hits you square. You with me?
Mm-hmm.
So the deal is that you can think of the hit as being pressure.
Okay.
So here, because the pressure's proportional to the kinetic energy and each has the same kinetic energy, the pressure is the same in each flask.
So we wouldn't consider the amount of moles, the difference in that?
You don't need to, because again, these guys are small and these guys are big.
Okay.
So if you have a bunch of small people hitting you, running into you, versus some big people running into you, it's going to be the same. So that's an interesting thing about gases, is that the pressure inside of a container depends on the temperature of the gas more than anything.
More than anything.
Isn't that what this says? Kinetic energy is proportional to the temp?
Yeah.
Okay. So that's B. C. The argon atoms have a greater RMS speed than the N2 molecules. So that's that velocity I was talking to you about, where we say smaller move faster. So RMS speed is how fast they move. So the answer is yes, argon is going to be greater than nitrogen for the RMS speed. RMS stands for root, mean, square. RMS.
I thought nitrogen would be faster.
Oh, I'm sorry. You're right. So no, nitrogen would be faster than argon. Thank you. See, you're learning. The nitrogen 2 molecules collide more frequently with the walls of the flasks than do the argon atoms. So do the nitrogen molecules collide more frequently than the argons? So meaning, like, does that nitrogen collide with the walls more than that argon?
Seems like they would,
Why?
because there's more of them.
No,
Faster.
that one hits the wall more frequently than that one. We don't care how many there are.
So yeah, because it's faster.
That's it. That's it. It's faster. Now, of course, if that one hits the wall more often than that argon, and there's more of these than those, then absolutely, in total, they will be hitting the walls of the container more. But this is about just an individual molecule versus atom. So here, you'll notice here, the N2, they should have written the A N2 molecule collides more frequently with the walls of the flask than an argon atom.
Okay.
So you would say yes, because the velocity, or we could say the RMS speed of nitrogen is greater than that of argon. All right, that's number 42. Okay, so calculate the RMS speed for carbon monoxide molecules at 25 degrees Celsius. What is the ratio of this speed to that of argon atoms at the same temperature? So you need to know how to calculate RMS speed. And let's see, it looks like this. So this is root mean square speed. And it is equal to 3 RT over the molar mass. And you can guess that the temperature is Kelvin. M is the molar mass. And R is a totally different value that I use so little that I've never memorized it. So let's look that one up. It's like 8.2 or something like that.
I thought it was 8.314 joules.
Well, I would say that if I guessed it was 8.2, that's pretty close to 8.3, right?
Mm-hmm.
So I'm going to say, hot damn, I did pretty good. So what page did you find that on?
I don't know. I have it in my notes. Probably 469.
Somewhere around there, yes. Yes, there it is. 8.3145 joules per K.
Per K per mole.
Per mole.
Okay.
Yes. Oh, and I see that I forgot my square root here also.
Where? Oh.
Okay. All right. And we should say that the molar mass, if you take a look on page 470, the molar mass, you want kilograms per mole so that things cancel out with joules.
For the equation though in the book, it says that the U is also squared, but it's the square root of that. Those doesn't make sense.
Oh, I'm sorry, I forgot that part. Boop.
Okay. Seems, I don't know.
Okay, so this is the speed.
Okay.
This is the square speed. And this is the mean square speed. And this is the root mean square speed. So that's the origin of each little part here.
Okay.
So square means squared, right?
Yeah.
And what does mean mean? What's another word for mean from statistics?
Average.
Average. So you square all of the speeds and then you average them. And then when you average them and then take the square root of that, you've got basically the average speed.
Yeah.
Now, it's not the average speed, it's the root mean square speed. But I like to think of it as like the average speed. So why do we go through all of this and do the root mean square speed rather than the average speed? And the answer is, I don't know. You would have to ask a physicist.
Yeah.
They understand this crap. I don't. All I know is that that looks like the average speed to me. But with a twist, fine. Put your twist on it. I can deal with it. Okay, so for this formula, you need the molar mass to be kilograms per mole so that the units cancel. And your R is 8.3145 joules per K per mole. And temperature has to be in Kelvin.
So
Fair
for
enough?
This one, for this equation, molar mass has to be in kilograms per mole.
Right, because if it's not, it won't cancel.
Okay.
Remember, a joule is a
Right.
kilogram meter squared per second squared. And here, if R is a joule per kilogram per mole, that means in this equation, you've got 3 times kilogram meter squared per second squared. That's the joule part, all over K times mole. And then all of this over kilograms per mole. And so what happens here is the moles cancel. Oh, I forgot the temp. The temp is in Kelvin, so the temps cancel. The kilograms cancel. And then you have meters squared over seconds squared, right?
Yeah.
And what happens when you take the square root of meters squared over seconds squared? You get
The squares go away.
meters per second, right?
Yeah.
And meters per second sounds like a velocity, right? Yeah. So basically the average velocity, but not really. It's the root mean square velocity. And then just to be true to physicists, you can't call it root mean square velocity. You have to call it root mean square speed, because speed does not have a vector attached to it, but velocity does. So for instance, let's say you were driving from one town to another at 50 miles per hour. So like Eureka to Fortuna, you're going 50 miles an hour, and that's your velocity. That means when you go from Fortuna to Eureka, you're driving at negative 50 miles per hour.
Okay.
Because velocity, in that case, we're defining as going south. That's positive, going north is negative.
So it involves which distance or direction we
It involves direction, just like heat being endothermic and exothermic.
Yeah.
Speed says, forget that. Just how fast are you going?
Yeah.
Okay, so that's why I call it speed. Because we're not adding direction to the molecules. We're just saying whatever direction they're going in, this is how fast they're going.
Okay.
Okay, so now we know all of that. Let's do a calculation. So we're going to do The root mean square speed is 3 RT over the molar mass. So CO2 is going to be 12.01 plus 32 . 44.01 grams per mole, right?
Yeah.
But we want kilograms per mole. So what are we going to multiply by?
Um,
1 kilogram over 1 times 10 to the third grams.
yeah.
Okay. So the way they do this in the book, they just say 44.01 times 10 to the minus 3 kilograms per mole. So they take that and put it in the numerator and leave it as 3, but negative 3. Are you with me there?
Yeah.
Okay, so now we can plug our numbers in. We've got 3. R is 8.3145 joules per K per mole. T in this case is 25 degrees Celsius plus 273.15, right?
Yeah.
So 298.15 K. And because this is 25 and good to the ones, this is really only good to the ones, but we're not going to round yet. The molar mass is 44.01 times 10 to the minus 3 kilograms per mole. And we can try to estimate this. Should we give it a try?
No.
Are you afraid?
Yeah.
I am too, kind of, but I'm willing to give it a try.
Okay, you can try.
Well, tell me this. How many times does 8 go into 44? 8.3.
6.
Five times?
Okay. 5.
Okay, so we have 5 down here and 3 up there. How many times does 5 go into 298? Well, I don't want to know, but it goes into 360 times, right?
Yeah.
Okay. What's 60 times 3?
180.
Okay, 180. And then this 10 to the minus 3 becomes 10 to the positive 3, right?
Yeah.
So that's 180 times 10 to the positive 3. Now that's 180,000.
Yeah.
Now here's the hard part. What's the square root of 180,000?
I don't know.
Neither do I. But I do know this. This is the same as saying 18 times 10,000, right?
Yeah.
Okay. And the square root of 10,000 is 100.
Right.
So what times what is 18?
9.
No, I think 4 times 4 is 16, right?
Oh, yeah. I was adding.
So I think the answer is going to be around 400.
Okay, let's give it a try.
Let's give it a try. Okay, so when I multiply all that stuff on the inside, I get 168,982, and we guessed 180,000, which I say is not bad. And now I'm going to take the square root of that. Oh,
How do you?
my calculator doesn't do that. So here's what you have to do with my calculator. I do the square root, and then it gives me the parentheses. And now I do 3 times 8.3145 times 298 0.15 divided by 44.01 second EE negative 3, end my parentheses, and done. Whoa, look at the answer.
Wow.
And what did we guess?
400-ish?
400-ish. 411. Dang. Good job. So how many significant figures are we allowed here? Because of this 298, we're allowed 3 significant figures. So 411. And what are the units? Meters per
Second.
second.
And how do we get that even though we don't have that in our equation?
Well, we do have it in our equation because if we look at the above, do you see how the K's cancel?
Yeah.
Do you see how the moles cancel?
Yeah.
Well, we're left with kilojoules and kilograms, right?
Yeah.
And the way that works is that a joule is actually a kilogram meter squared per second squared divided by that kilogram. What happens to the kilograms?
Cancel.
Okay, but we're also doing the square root of this. So what's the square root of a meter squared over a second squared?
Okay, meters per second.
So that's why it's important for you to understand that you need to have the molar mass in kilograms per mole so that you don't need to worry about things canceling. You just know you're going to get meters per second because we just did it.
There was something from chapter 6 just like this.
Chapter 6?
I think so.
Not with the root mean square speed.
No, I mean with the joules and needing it to be in kilograms.
That was the wave equation.
Yeah,
De Broglie wave equation. You needed to have the mass in kilograms to make it work.
Right.
Because Planck's constant is joule second.
Yeah.
So yeah, same concept, precisely. Okay, so that's number 44. Now, argon gas is 10 times denser than helium gas at the same temp and pressure. Which gas is predicted to effuse faster? So here we need to understand what effusion is and what diffusion is. So here, if you have a gas in a box and you open up that box, so here's my gas particles. Naturally, the gas particles will start spreading out, right?
Yeah.
This is called diffusion.
Yeah.
If you have a gas and we have the particles in here like this, and then all of a sudden we make one of these walls porous, so there's holes in it.
Okay.
What's going to happen to these gas particles? They're going to make it through the holes, and eventually they will end up, maybe one is still in here or not, but they end up getting out into the room, so to speak. Are you with me there?
Yeah.
This is effusion. So the big difference is diffusion, you don't have little holes you're going through. Effusion, you do. That's it. That's the difference. Now, when we talk about diffusion and effusion, what's going to effuse or diffuse faster? Small gas particles or large ones?
Small.
Why? You're right. Why?
Because they move faster.
Because they move faster. Has nothing to do with their size in the hole. Nothing to do with that. Has to do with that, well, you know what? They're going to move around in the box faster. So they're likely to hit a hole faster and effuse faster.
Makes sense.
Okay. So that's what effusion is all about.
Okay.
Now, they say argon gas is 10 times denser than helium gas at the same temp and pressure. Which gas is predicted to effuse faster? How much faster? So here's what they use for that effusion. So we're going to do this. This is going to be the root mean square speed of argon is equal to 3RT over the molar mass of argon, correct?
Yeah.
And if we do the same thing for helium, we're going to get almost the same equation, but it's going to be the molar mass of helium, right?
Yeah.
Okay. Now this velocity tells you which one effuses faster, right?
Yeah.
So here, a very simple way to say this is that the rate of argon, and call this the rate of helium, the rate of effusion. Okay, so here you can see that the rate of effusion is kind of inversely proportional to the molar mass, right?
Yeah.
So that means smaller molar mass, smaller number on the bottom, means a bigger value here on the inside, and therefore a bigger rate. Large value on the bottom means a small value here, and therefore it effuses slower. So when it says which gas is predicted to effuse faster, we would say that helium effuses faster simply because it has a smaller molar mass.
Okay.
Fair enough?
Yeah.
Okay, so the question says how much faster? So here's what we're going to do. We're going to take the rate of helium over the rate of argon and figure out which one effuses faster.
Okay.
Now, here is the formula we use. Are you ready?
Yeah.
We use that formula.
So we divide the mass of
The
one gas.
molar mass of argon, which is on the bottom over here, but it's on the top over here. And we're going to use the molar mass of helium on the bottom over here, even though the rate is on the top. Let me show you how I get that equation here. And then after that, you just want to write it down on your index card.
Yeah.
So we've established that the rate of gas A is equal to 3RT over the molar mass of gas A, right?
Yeah.
And the rate of gas B is 3RT over the molar mass of gas B, correct?
Yeah.
Well, what happens if I say, you know what? I'm going to divide the rate of A by the rate of B. That means I'm going to divide this by that.
Okay.
Now, since they're both under the square root, I can do this. I can put them all under one square root. Now, you were taught in math that when you have a fraction in the top and the fraction in the bottom, what do you do with the fraction in the bottom? You do this. you invert it and multiply it by the top. Do you remember that?
Yeah,
Okay, so what happens to the 3?
cancel,
What happens to the R?
cancel,
What happens to the T?
cancel.
So this becomes the square root of the molar mass of B over the molar mass of A. So here, even though the rate of B is on the bottom, the molar mass ends up in the top
Okay.
because of the way this equation is written here.
Okay.
So do you want to spend time figuring out that rate A over rate B is the molar mass of B over the molar mass of A? Do you want to figure that out every time or just write that down?
Just write that down. So we can just
Okay.
use that for the
Now,
exam.
there's another caveat to this equation.
Okay.
The rate is going to be the moles per minute or maybe moles per hour, but some unit time, that's the rate, okay? Or for the rate, we can use volume per minute or volume per time.
Okay. So
And that's because in a case like this, the volume is proportional to the moles.
yeah.
And so it must be these types of units for the rate
Moles or volume
per time.
per time.
Okay. All right. So now we can finish this one off here. We're starting with rate of helium over the rate of argon is the molar mass of argon over the molar mass of helium, square root of that. The molar mass of argon is 39.9 something.
948.
39.948 grams per mole. And notice here,
Can we just not
I'm not concerned with kilograms
or
per
not?
mole.
Okay.
And the reason why is because when I plug these numbers in here, 4.0026 grams per mole,
They cancel.
if I had calculated kilograms per mole and I had calculated kilograms per mole, what would happen?
They would cancel.
Okay. And now that I didn't do that, what happens?
They still cancel.
They still cancel.
Okay.
Okay. So what is 40 divided by 4?
10.
What is the square root of 10?
I don't know.
Well, what is 1 times 1?
1,
What's 2 times 2?
4,
What's 3 times 3?
9,
What's 4 times 4?
16.
So what times what is 10?
3.5.
Well, I would say no, since 9 is so close to 10,
Right. So
I'd say it's really close to 3, like 3.1, 3.2.
yeah.
Okay, let's give it a try. Oh crap, I got to do square root first.
Yeah. Me too.
Square root.
3.1.
I'm going to try something here. I'm not going to put a parentheses on the end and see if it works.
It does.
It didn't for me.
Oh.
I got 0.3.
That's not right.
No, that's not right. That's why I'm glad we estimated, right?
Yeah. So do we just decide the unit? I'm confused on that part.
There are no units because it's a ratio.
But you had said that the rate.
Okay, so we get a 3. And our problem is we use so many units here that we actually get 5 zig figs.
Yeah.
So the rate of helium compared to the rate of argon is 3.15. So we would say the rate for helium is 3.1592 times greater than the rate of argon. So the units here are this rate of helium over the 1 rate of argon. So that's what we're looking at. Here's how fast the helium rate's 3.1592 compared to every 1 for argon.
Yeah.
So that would be 3 atoms for every 1 atom of argon, or 3.1 liters for every 1 liter of argon.
So that's how much of helium is diffusing.
Yeah. So when they want the rate, when they say how much faster, you say, well, it's 3 times faster. Okay. So they're not really asking you for a specific number. It's kind of like a, 2 people, who's walking faster? Well, they're walking 3 times faster. Who's running faster? They're running 3 times faster. They're not asking you for how fast, just how much faster. Okay.
Okay.
All right. A sample of uranium fluoride is found to fuse at the rate of 17.7 milligrams per hour. Under comparable conditions, gaseous I2 fuses at the rate of 15.0 milligrams per hour. What is the molar mass of the uranium fluoride? And they give you a hint that the rates must be converted to moles per time, because they didn't give us moles per time, they gave us milligrams per time. So if they're going to tell us to convert that to moles per time, let's do it. All right. So the uranium fluoride, and they ask us, what is the molar mass of the uranium fluoride? That means we don't know the formula. You with me?
Yeah.
Okay, so this is going to get tricky.
Yeah.
However, we can get the molar mass of I2, right?
Yeah.
So I2, we've got 15.0 milligrams per hour. Does that sound right?
Mm-hmm.
Okay, and we know that for 1,000 milligrams, there is 1 gram. And for I2, there's, I'm going to go to the 100th. We've got 196 or 126.90 times 2. We know that there's 250, that should be on the bottom, 253.80 grams per 1 mole. And so what we're going to be left with here is if the milligrams cancel and the grams cancel, we're going to have moles per hour. Fair enough?
Yeah.
Now, this is a tough one to estimate, but we know darn sure it better be a lot smaller than 1, right?
Yeah.
And I get 5.91 times 10 to the minus 5 moles per hour. Are we good to go there?
Yeah. Yeah.
Okay. Now, we know that the rate of I2 over the rate of the UF and here I'm putting question mark, because we don't know what the subscripts are, right?
Yeah.
Is equal to the molar mass of U question mark F over the molar mass of I2.
Right.
Okay,
So
so where do you want to go from here?
well, we know the molar mass of I2.
Okay, the molar mass of I2 we already have as 253.80 grams per mole. And now we have the rate is 5.91 times 10 to the minus 5 moles per hour, right?
Yeah. So
So let's look at this
I
U question mark F question mark, and let's figure out the rate the same way we did up here. So we've got 17.7 milligrams per hour, right? Times 1 gram over 1,000 milligrams, right?
yeah.
Times 1 mole over what?
Mm,
We don't know, do we?
no.
Let's call it X, 1 mole per X. And that would give us the moles per hour. And that's what we want, right?
Yeah.
Well, here, what is this? This is X mole or X grams per 1 mole, right? And
What?
this should be grams right here.
Mm-hmm.
This is X grams over 1 mole, isn't it? The molar mass?
Yeah.
Okay. Aren't these the same thing, but a little bit different?
Yeah.
So can I write this, that this UF rate is 17.7 milligrams per hour times 1 gram per 1,000 milligrams times 1 over the molar mass of UF. Can I write that?
Yeah.
Okay, and what do we get here? We get 1.77 times 10 to the minus 2, I think. I'm going to do it in my calculator. To the minus 2 grams per hour and divided by the molar mass of UF. Because that doesn't cancel with anything, does it?
No.
And actually, this is going to be grams per mole, right?
Yeah.
The molar mass.
Molar mass. Yeah.
So I think I want to leave this gram here and leave that as molar mass. So this is a really tricky, but now we have some things that we can do here. So the rate of I2 is 5.91 times 10 to the minus 5 moles per hour. The rate of UF is 1.77 times 10 to the minus 2 grams per hour divided by the molar mass of UF. The molar mass of UF is, well, the molar mass of UF, and the molar mass of I2 is 253.80 grams per mole. So that's everything we have. And we have this equation here. And we have this equation. So we're now going to put things in. So I'm going to put 5.91 times 10 to the minus 5 moles per hour. Are you with me there?
I'm just watching.
What am I going to put in for the rate of UF? This 1.77 times 10 to the minus 2. And actually, now that I think about it, since this is grams per mole, I'm going to go ahead and cancel these grams and put mole per hour.
Okay.
Is equal to, oh, and I forgot the molar mass of UF, is equal to the molar mass of UF over 253.8 grams per mole. So here I have everything I need. Do you see that the moles per hour cancel?
Yeah.
Okay. And all I need to do now is I need to clean this up a bit. So let's clean it up a bit. What's 5.91 times 10 to the minus 5 divided by 1.77 times 10 to the minus 2? I'm going to do that first. There's probably a more clever way to do this, but I don't have it on me right now.
Yeah, I feel like there's got to be a more straightforward way.
So if I take these two, I get 3.338 times 10 to the minus 3. And then that's times the molar mass of UF is equal to the molar mass of UF over 253.8 grams per mole. And here, this is going to be grams per mole too, right?
Yeah.
So these cancel.
Right.
So now I have 3.338 times 10 to the minus 3 times the molar mass of UF is equal to the molar mass of UF over 253.8. So what are we going to do? Do you like working with squares? Square root, I mean?
Yeah.
So how about we do this? Let's square this side and let's square this side.
Okay.
So I'm going to square this 3.33. And that should be a 9. And I get 1.11 times 10 to the minus 5. And I get the molar mass of UF squared because I have to square everything inside of there, this and that. You with me there?
Yeah.
Okay, and here I'm going to get the molar mass of UF over 253.8.
Okay.
So now, if I have 2 of these on this side and 1 on this side, what happens?
One of them canceled.
One of them cancels. And so now I get that the molar mass of UF is going to be equal to, I'm going to divide each side by 1.11 times 10 to the minus 5, right?
Yeah.
So I get the molar mass of UF is 1 over 253.8 times 1 over 1.115 times 10 to the minus 5. Oops, I have a problem. Having trouble with my calculator. and I get 353. Is that what you got?
I didn't do it.
Well, you should do it.
Okay. $353.
Okay. Now here's the dealio. We know that uranium is 238. We know that this UF is 353. The difference is
115.
115. And we know that each fluorine weighs how much?
I don't know. 19.
So we're going to do 115 divided by 19 and see what we get. And we get 6.07.
Yeah.
So how many fluorines do we need to make 115?
6.
So UF6 is probably the answer.
Okay.
So is there a way for us to check this answer?
Yeah, I'm sure.
Sure. We could go back to the equation rate of iodine over the rate of UF6, since we know what it is now, right?
Yeah.
Is equal to the square root of 353 over 252.8 or something like that, 3.8, right?
Yeah. Mhm.
And here, when we do this value, we get 353 divided by 253.8. And then I take the square root of that, which I didn't do to begin with, darn it. Okay, so for this side, I get 1.179.
Yeah.
And we already know that the rate of I2 is right here. .91 times 10 to the minus 5 moles per hour.
Mhm.
And we know that the rate of the UF was 1.77 times 10 to the minus 2 milligrams per hour, right?
Yeah.
And we're going to multiply by 1 gram over 1,000 milligrams. And we're going to multiply by 353 moles per 1 gram. So we get the rate in moles per hour. Oh, I did this wrong. It's not 353 moles per gram, is it?
I don't know.
It's 353 grams per mole, right?
Yeah. Yeah.
And so I get 5.014 times 10 to the minus 8 moles per hour. So we're going to take this 5.91 times 10 to the minus 5 moles per hour and divide by 5.014 times 10 to the minus 8 moles per hour and see what we get. Hopefully this works out. And it didn't work out. I did something wrong. I'm not sure what.
What did you get?
I got 1,178.
Okay.
Is that what you got?
Yeah. Something with the decimal place.
So let me see if I copied something down incorrectly. This is the only thing I'm not sure how I got. And I may want to do that one again. But I think that's the right answer. I really do. Well, I think our check didn't work out, but I'm going to go with the UF6. And I think there probably is a easier way to do this.
So,
And what it has to do with is this. Couldn't we say that the rate for I2 is going to be 17.7 milligrams per hour times 1 over 1,000 times 1 over the molar mass of I2?
Yeah.
Right? So we could do that, and we could say that the rate of UF is 15.0 milligrams per hour times 1 gram over 1,000 grams times 1 over the molar mass of UF. So those are the rates. Fair enough?
yeah.
So that means we can say that the rate of I over the rate of UF is 17.7 milligrams per hour times 1 gram over 1,000 milligrams times 1 over the molar mass of I2 over 15.0 milligrams per hour times 1 gram per 1,000 milligrams times 1 over the molar mass of UF. So I've basically taken this and put it here. And I've taken this and put it here. Now you might be wondering, why am I doing all of that? Well, let's take a look. What happens to the milligram here and the milligram here?
Cancel.
What happens to the hour and the hour?
Cancel.
What happens to the 1 gram over 1,000 milligrams and the 1 gram over 1,000 milligrams?
They cancel.
They cancel. So we're left with the rate of I over the rate of UF is equal to, now these two end up being 17.7, that's that. And what happens when you have a fraction in the denominator? You flip it, right?
Mhm.
So I'm going to put the molar mass of UF and 15.0 times the molar mass of I2. Because if I take this, which is 15 over 1, and flip it, I'm going to have molar mass of I2 times 15. All right, do you kind of follow that?
No.
Okay, well, you don't need to. What I mean by that is, do you see how with these two, it ends up being the molar mass of UF over the molar mass of I2?
Yeah.
Fair enough. What does this end up being? It ends up being 17.7 divided by 15, right?
Yeah.
So let's just do that. What's
Okay.
17.7 divided by 15? It's
Mm,
really close to 1, isn't it?
a little more than one.
So I get 1.18 times the molar mass of UF over the molar mass of I2.
Okay.
Is that what you got?
No, I hadn't finished.
Oh,
I was still writing everything down.
okay. Well, for this part, we're just dividing 17.7 by 15.
Yeah. Okay. Yeah, that's what I got.
Okay. The other thing we know is that this equation here, 1.18 times the molar mass of UF over the molar mass of I2 is equal to the square root, because we have I2 on top, the molar mass of I2 on the bottom, and the molar mass of UF over here on top. Right?
Yeah.
So how do we, since we don't like squares, what are we going to do to this?
Square both sides.
Okay, so if I square this side, I get 1.18 squared molar mass of UF squared over the molar mass of I2 squared. So I'm squaring every little thing in there, right?
Yeah.
And here I'm going to square this, which is going to be that over that.
Yeah.
So what happens to one of the molar masses of UF?
It cancels.
What happens to one of the I's, I2s?
Cancel.
So we get 1.18 squared times the molar mass of UF over the molar mass of I2 is equal to 1.
Yeah.
So that means that the molar mass of UF is going to be the molar mass of I2 divided by 1.182 squared, I think, if I did this right. I may have just got myself into trouble, but let's find out. And I get 182, which cannot be the right answer.
Hmm.
How do I know that can't be the right answer?
I don't know.
Well,
Because
what's the molar mass of uranium?
I don't remember what you had.
238.
Yeah.
So can the molar mass of uranium plus fluorine be less than 238?
No.
So I'm not sure what I did wrong here, but I have the feeling. Let's see, rate of I2. Oh, I see what I did wrong. See that?
Yeah. 15.
That's 17.7. See that? That's 15.0.
Oh,
So
yeah.
that means this is 15.0 and this is 17.7, which means this is really 15.0 over 17.7. So it's really 1.18 on the bottom. And that means when we go over to this side, it's supposed to be 1.18 here. So the molar mass of UF is the molar mass of I2 times 1.18 squared. Let's see what we get there.
$353.
353. So yeah, it works out. So just so that you can see it all in one place, here we go. Are you ready?
Yeah.
So the rate for I2 is equal to 15.0 milligrams per hour. And that's with me carefully reading the problem.
Yeah.
Times 1 gram over 1,000 milligrams times 1 over the molar mass of I2. Now I'm going to divide this by the rate of UF. So that means I'm going to divide all of this by 17.7 milligrams per hour times 1 gram over 1,000 milligrams times 1 over the molar mass of UF.
Okay.
So when we clean this up, we get the molar mass of UF over the molar mass of I2 because of all this stuff. These cancel, milligrams per hour cancel, and 15 divided by 17.7 is 0.8475. Now this number is a little different than that 1.18, and that's because the 1.18 was in the bottom.
Yeah.
And 1 over 1.18 is 0.8475. Now, we know that this 0.8475 molar mass of UF over the molar mass of I2 is equal to the square root of the molar mass of UF over the molar mass of I2. Now, how do I know to put this one on the top? It's because the rate is on the bottom.
Okay.
You remember how they're kind of opposite?
Yeah.
So now what do we do with this? We square each side. So now I've squared each side, and I'm going to go ahead and do this squared. Is there a square button on this calculator? Yeah, there is. So when I square this, I get 0.71818 molar mass of UF squared over the molar mass of I2 squared is equal to the molar mass of UF over the molar mass of I2. So how do we simplify this part?
We cancel 1 molar mass of UF and 1 molar mass of I2.
So now we have 0.71818 times the molar mass of UF over the molar mass of I2 is equal to 1. And so we get 353 grams per mole. So do you see how this becomes that?
Yeah.
And then here, I'm simply putting the molar mass of I2 in, and we get 353.
Right.
So I'm not sure how I screwed up the check that we did later, but I screwed up the check somehow or other.
Are you checking again?
No, I'm just checking something real quick to see if I know what I screwed up.
Oh, okay.
I just had a thought that when I screwed up, didn't we get a number of like 1,179 or something like that?
Yeah.
So I'm kind of curious what the square root of that is. And I'm having a lot of trouble with my calculator. I can't do the square root of 1,179 for the life of me. Nope, that wasn't it. I'm not sure what I screwed up on the check. But you know how you were saying it seems like there might be a simpler way to do this?
Yeah.
This is the simpler way to do this, but it takes some complex thinking about ideas and what's going on.
Yeah.
See, it's not common sense to do this and put one above the other to see how things cancel. It's not common sense. It's something that you develop over the years. And that's why I didn't do this to begin with, is because it's a little too advanced.
Okay.
But on the other hand, once we've done this, then the rest of it is just algebra. This is the complex idea right here. Okay? So that was certainly a challenging one to do. Now, let me see if the next problem is not about effusion or diffusion. It's about ideal gases. And so maybe we better leave that until tomorrow or something like that. And just call it quits here, because we've been at it for like 2 hours.
Okay. So ideal gas laws tomorrow.
Oh, well, actually, whatever you want to do.
Yeah. That's fine. Yeah.
And but that's kind of what we're set up for next, is the ideal gas behavior versus non-ideal gases.
Right. And then we only have one more chapter left,
Yeah, chapter 23.
and then we're done.
Yeah, I've already posted the homework for chapter 23.
Okay.
I've posted the lab for chapter 10. You're going to be watching videos instead of actually doing the gas lab at home.
For the galvanized meal.
Yep.
Okay.
So there's 4 videos. There's the lecture video, there's the demonstration video, then there's 2 addendums.
Okay.
Yeah, and overall, I think that the whole process is probably maybe an hour of videos.
Okay. And then our
And
lab.
yeah, and we're only going to be doing 1 lab this week for that type of stuff, not 2 labs.
All right. And then one
And
lab next week.
there's going to be 1 lab next week. And that'll be the last lab.
Okay.
And I'm hoping tonight, or at least tomorrow, I'm trying to finagle this so that on these weeks where you only have one lab, you'll also be working on your lab report.
Yeah.
But I want to give you an example of what I want in the lab report so that you can do it.
Right.
And once I put that example up, you'll get a week to do it.
Okay.
Kind of
Yeah.
the same thing with the labs. Once I put it up, you get about a week to do it.
Do you have any practice final exams,
I don't have any practice final exams.
like in Chem 2? I think.
Yep, I don't.
Okay.
And time-wise, I'm just running out of time, so I'm not going to have time to make a practice exam.
What about, would Chem 2's practice exam be any helpful? Any help?
Yeah, but I don't know how to import it. And I also don't want you to think it's going to be that easy because it's not.
Oh, okay.
The Chem 2 practice exam and final exam is a lot easier than the Chem 1A.
Hmm.
Like the Chem 2 practice exam doesn't have any valence bond theory or molecular orbital theory in it.
Yeah.
It also doesn't have molecular geometries past having 4 things.
Right.
There's no octahedral in Chem 2. There's no trigonal bipyramidal in Chem 2. In Chem 2, I think we did some partial pressure stuff, but not much.
How do you suggest we study for it?
I would look at the old quizzes. I think they're still available, that you can still look at them.
Okay, that's helpful.
But the quizzes are a great way to practice because they are multiple choice.
Yeah.
Okay. That's about that. It's been too long now. We've been on here for more than 2 hours.
Alrighty. See you tomorrow.
Yes, but not for 2 hours. But clearly, I enjoy doing this kind of stuff. Otherwise, I wouldn't have been on that long.
That was that
And-
last question. Don't blame me, please.
No, I'm not blaming you. I mean, it's kind of neat to do. With Rebecca, we were doing number 40 and we ended up going really long because number 40 was interesting.
Oh, okay. Yeah.
And then after we got off the Zoom, I then thought, oh, well, why don't I just do it this way?
Yeah.
And that's why I started number 40 with you, so that I could do it this way.
Right.
All right.
Okay.
We'll see you tomorrow. Have a good day.
You too. Bye.
Bye.